Electrolytic ground in a printed circuit board, or PCB, design refers to a specific layer of the board that is connected to the negative terminal of the electrolytic capacitors in the circuit. Its primary function is to provide a low impedance path for high-frequency currents to flow back to the power supply. This minimizes noise and electromagnetic interference, often called EMI. Electrolytic ground is typically not explicitly specified in the code of the circuit. It is usually not assigned a dedicated symbol or signal name in the design software. Instead, it is automatically generated during the PCB layout process based on the rules defined in the PCB design guidelines. When designing electrolytic ground, several considerations are important. Firstly, low resistance. The electrolytic ground layer should be designed with low resistance to minimize voltage drops and ensure proper current flow. This is achieved by using wide traces and multiple vias to connect the ground plane to the electrolytic capacitor terminals. Secondly, adequate connection. All electrolytic capacitors should be connected to the electrolytic ground layer through short, direct traces. Thirdly, isolation. Electrolytic ground should be isolated from other ground planes to prevent ground loops and noise interference. Fourthly, star grounding. For optimal noise reduction, electrolytic ground should be connected to the power supply ground using a star grounding topology. This means that each electrolytic capacitor should have its own dedicated trace connecting it to the power supply ground. Proper implementation of electrolytic ground provides several benefits. One benefit is reduced EMI. Low impedance paths for high-frequency currents minimize noise and EMI emissions. Another benefit is improved signal integrity. Reduced voltage drops ensure that sensitive signals are not corrupted by noise. A further benefit is increased efficiency. Reduced resistance in the ground path improves the efficiency of the circuit by minimizing power loss. The design of the electrolytic ground involves several key aspects aimed at minimizing impedance and noise. Firstly, the ground plane itself. The ground plane should be as solid as possible, minimizing cutouts and voids. This provides a large, continuous conductive area for current return. Secondly, trace width. Traces connecting components to the ground plane should be as wide as possible to reduce inductance and resistance. Thirdly, via placement. Vias should be placed close to component pins to minimize the length of the current path. Multiple vias can be used in parallel to further reduce impedance. Fourthly, capacitor selection. Electrolytic capacitors should be chosen for their low equivalent series resistance, or SR, and equivalent series inductance, or SL, characteristics at the frequencies of interest. Fifthly, decoupling capacitors. Additional decoupling capacitors can be placed close to integrated circuits, or ICs, to provide a local source of charge and reduce noise on the power supply rails. Sixthly, isolation techniques. Techniques like God rings and isolated ground planes can be used to isolate sensitive analog circuits from noisy digital circuits. Seventhly, impedance control. For high-speed signals, impedance control techniques such as microstrip or strip-line routing can be used to minimize reflections and signal distortion. Eighthly, grounding strategy. A star grounding strategy, where all ground connections converge at a single point, can help to minimize ground loops and noise coupling. Ninthly, power supply filtering. Filtering the power supply can reduce noise from the power source. Tenthly, PCB stackup. Optimizing the PCB stackup can improve signal integrity and reduce EMI. This includes placing ground planes close to signal layers and using controlled impedance routing. These design considerations collectively contribute to creating an effective electrolytic ground, ensuring signal integrity, and minimizing noise in electronic circuits. The design rules and guidelines for PCB often dictate the specifics of ground plane design to ensure optimal performance and compliance with electromagnetic compatibility, or EMC, standards. The design and implementation of an effective grounding strategy are crucial for ensuring the proper functionality and reliability of electronic circuits. Poor grounding can lead to a variety of problems, including noise, signal distortion, and even circuit malfunction. Therefore, understanding the principles of grounding and following best practices is essential for any electronics engineer or PCB designer. It is important to remember that electrolytic ground, while typically associated with electrolytic capacitors, is just one aspect of a comprehensive grounding strategy. Other types of ground, such as digital ground and analog ground, may also be present in a PCB design and must be carefully managed to avoid conflicts and ensure proper operation. When designing a PCB with multiple ground planes, it is important to consider how these planes are connected and isolated from each other. A common approach is to use a split ground plane where different sections of the board have their own dedicated ground planes. These ground planes can then be connected at a single point, often near the power supply, to minimize ground loops. Another important consideration is the placement of components on the PCB. Sensitive components, such as analog circuits and high-speed digital circuits, should be placed close to the ground plane to minimize noise and interference. It is also important to keep traces short and direct to reduce inductance and resistance. In addition to the design considerations mentioned above, there are also several tools and techniques that can be used to analyze and optimize the grounding performance of a PCB. These include simulation software, which can be used to model the behavior of the ground plane and identify potential problems, and measurement equipment such as network analyzers, which can be used to measure the impedance of the ground plane and verify its effectiveness. The specific techniques used to implement electrolytic ground may vary depending on the application and the design requirements. However, the basic principles remain the same. By following these principles and paying careful attention to the design considerations, it is possible to create an effective electrolytic ground that minimizes noise, improves signal integrity, and enhances the overall performance of the circuit.